Okay, good evening, everyone. So this is the fourth life solving session for the course Nanomaterial and Their Properties. Indeed. All right, we'll briefly go over the topics covered in the video lecture. The next session is on 25th. So we have derived how this parameter changes with the radius in last class. Right. So this delta A 4 column, which is also function of diameter D, A intersection P, and 3. So according to this relation, if you increase D, your lattice parameter decreases. So, but if you increase diameter, lattice parameter is actually increasing. So that's because your interfacial energy is also a function of D, and this is a more dominant effect. So overall, when you increase D, your A is also increasing. These are very annotating. Okay. Yeah. Your lattice parameter is function of both the interfacial energy and the particle size. So, when you decrease the particle size, the lattice parameter is also decreasing. Okay. Next, he I don't think he did the derivation, but how do you get this value? So if you assume a cluster, if you assume a spherical cluster made up of lots of atoms, okay, and spherical atoms, you assume all these are same size atoms. There are any number of atoms inside this cluster. The radius of these atoms is RA. This value, this is your RA. And from the center of the cluster to the boundary, you have RC, which is the radius of the cluster. Now you have total volume of this cluster you can write as 4 by 3 by R C radius of cluster cubed. Okay. And this is equal to the volume of each atom VA into total number of atoms. This is just from the geometrical calculation of the cluster, and this is you get this value from the individual atoms. Here is not, you're assuming it's perfectly packed. Okay. So now, for your Na, the Va term, again, you write these spherical particles of 4 by 3 spherical atoms, so 4 by 3 pi r A cubed. So, if you compare both sides, 4 by 3 pi rc cubed is equals to Na times 4 by 3 pi r A cubed. 4 by 3 pi cancels on both sides, and you're left with Na is equals to Ra cubed divided by Rc cubed. Yeah, this is how you get this value. Next, so now if you assume there's this surface of these atoms on this cluster, so you have atom sitting on the surface. So your surface for the cluster becomes equal to 4 pi rc squared. This is the radius of the cluster. So this is total surface area of this cluster. Now you had this relation Na is equals to Rc cubed divided by Ra cubed. From this you can see that Rc squared is equals to Na to the power 2 by 3 Ra cubed. Just take cube root on both sides and do square. So this is how Rc and Ra are related. So you can substitute the value of Rc here. So we get Sc is equals to 4 pi Na to the power 2 by 3 Ra uh, square Ra square. Okay, and now you can write, and its number of atoms on the surface as ns. So this is the total surface area, and which is Sc divided by surface area of an atom. Sc, whatever you want to call it. So you have 4 pi Na 2 by 3 Ra square divided by this radius, which is pi surface area. is area, cross-sectional area of the atom. Cross-sectional area is only pi r square. R square, R square cancels out and you get 4 by 4 pi and to the power 2 by 3 is your number of atoms sitting on the surface. And to get the fraction of atoms sitting on the surface, you just divide by Fs is equals to Ns, your atom sitting on the surface divided by m, which is 4 pi Na 2 by 3 divided by Na, where 4 pi n to the power minus 1 by 3. Yeah, pi got cancelled here. So for Na to the power minus 1 by 3. So this is Na is the number of atoms in a cluster. And your Ns is number of atoms on surface. Let's have a look at this relation. So as you go down, your Fs is equals to N is by 3. So relationship between Fs and this should be linear. This is a theoretical calculation needed. However, this is only true when you have fairly large particles, because as you go down to smaller particles, your spherical approximation does not hold true. Like the gold 55 becomes cube octahedron, and yeah, as you go down, as you increase the cluster size, your fraction of surface atoms becomes really small. So yeah, they're going this way. These are your large clusters, large clusters in this region. Up till this point, you can approximate it using this equation. After that, you need to uh, do calculation for individual shapes, which would depend on the crystal structure of the material. Sorry about that. Okay. So next is how your crystal structure affects your particle shape, where we have introduced magic numbers. So if you just have one layer of atoms, so suppose like gold, you have FCC structure. So FCC is a closed packed structure, so you have six atoms occupying. And this is your first layer, and the next three atoms are sitting over here, and ours is a different color. So there are three atoms sitting this way, and similarly, three atoms are sitting below this plane. So underneath, underneath this dashed circles, there are three atoms sitting underneath this layer. So, so if you just see the central atom, this one, the first one we draw, black one, it's connected with, bonded with six atoms and it hits on plane. So one, two, three, four, five, six. And the next three, one, two, three, on the top of the layer above it, and there are three below it. Uh, one, two, three. So if you sum them, you get six plus three plus three, and the atom itself plus one, so you get 13 atoms in first cluster. Okay. Similarly, if you do the second layer, then you'd have like, a central atom and this one populate another layer according to the FCC crystal orientation, and you fit the atoms above it, below it, and do the calculation. You get 55 atoms sitting in the next layer, 147, 309, and 561. So as you go up in the size of the cluster, you start seeing the actual shape of the particle. I think this is hydrogen. Okay, so that's how you get these magic numbers. So if you do the manual calculation manually, you can also uh, get an equation to get the number of atoms in the cluster. This is what we're calling the magic number. So for the first cluster, uh, we put k is equals to 1. So for k is equals to 1, the total number of atoms becomes 1 is equals to 1 by 3, 10 into 1 square minus 15 into 1 square plus 11 into 1 minus 3. What is it? 1 by 3, 10 plus 11, 3 minus 18. This sign should have been plus. Think you correct them to negative. You take plus, you get you get 11 plus 10, 21 plus 18 by 3. 39 by 3, 13. Yeah. So the correct formula is m star k equals to 1 by 3 and k square cube plus 15k square plus 11k plus 3. We can try another number, say k is equals to 2 and 2 times 1 by 3. 10 into 2 cubed is 8 plus 15 into 4 plus 22, 3. This becomes 80 plus 22 is 102 plus 3 is 105. 105 plus 16, 05 plus 60 by 3. 20, this is 55, 55. Think that was the second magic number, right? 55, yeah. This is the correct formula. Mm. And yeah, so this is every shell of atoms around the central atom contains nk number of atoms. Itself has some question what is the relationship between surface energy and the lattice parameter. Yeah. This is the lattice parameter and your gamma is your surface energy. So that's how they're linked related to each other. How do you obtain the magic numbers? We saw this formula m star k is 1 by 3 10 p cubed 15 k square 11k plus 3. How the size and the shape of the cluster structure depend on the nanoparticle size. The size obviously uh, as is increasing, the size will increase. Shape and structure, it will depend how what is the crystal structure of the atoms. So as you're going to higher uh, number of atoms in the cluster, you're getting more of the defined shape of the particle, which it will take. And as you go down, you will see more of the crystal, the FCC crystals, uh, the atoms arranged in the FCC crystal shape. Next he covered interfacial energy as function of orientation. So we have different for this FCC according to different directions. This is what the cross section view you will see. If you cut this along 111 plane, you'll see atoms sitting packedly together with each other. If you cut it across 200 plane, I think then you get your FCC case. Yeah, atom is sitting on the center. And if you cut along the 220 direction, 220 this direction, you get layers of atoms. How the interfacial energy changes as a function of orientation. Again, if you have you're cutting the plane, the atoms across a random direction, which is at angle theta, you're breaking bonds. So if you cut it flat, you'll only break the vertical bonds, and if it's completely vertical, you'll break the horizontal bonds. If it's at angle, then according to the broken bond model, this is the interfacial energy you get, which is function of theta. We saw this already in the class, how this energy depends on the theta as you change. Yeah. It's lowest at theta is equal to 0, which is I think this u over 2a. And then you had your Wolf diagram. So you have your crystallographic direction. So this is 1 0, 0 1 0, and something like out of plane will have 0 0 1. So to get the shape of the particle, what you do is draw the uh, at whatever angle theta, suppose this is for 1 plane, you draw this line and take the perpendicular at that point and reduce this for all of the thetas for all the directions. For 1 you'll have different theta, and you take the normal to this and do this for all the directions. And the area enclosed is your this is your Wolf plot, which gives you the particle shape. Um, these are the self-assessment questions. I'll go straight over to the practice questions. So calculate the number of broken bonds per unit area for a nickel crystal on 100 plane. For this, you need uh, what is the crystal structure of nickel? The nickel, I think, has actually structure. So, 100 plane. You have atom sitting on edge and one sitting on the surface. You cut it along 100, so along the x, it's 1. Y, so it's parallel to your y plane. So this is the change the color. I think, yeah, I'll draw it. This face center. This face is your 100 plane. Okay. So nickel is FCC. You know two things. Okay. So now how many atoms are sitting on the surface on this face? So you have one and one fourth here, four here, and that four here. So you get two bonds for this face. Okay. Surface atom density. Okay. The surface atom density. And this is side length A. The two bonds per unit area. So if you just imagine this atom, the next nearest neighbor for this one was this face center atom, this one, and this one. So if you imagine this atom, the next nearest atoms are this one, this one, this one, and this one. All are the four face center ones. So the next, how many bonds are broken for this one? So you have four broken bonds. So there are you have each surface atom loses four nearest neighbor atoms. Okay. But bond is shared between two surfaces, so we only count half of it. So bonds per surface atom is 2. So now the total bonds broken per unit area, N S N is equals to 2 times this NS, so 4 divided by A square. Another thing they haven't mentioned is the A of this nickel. It's around 3.52 angstroms. So 4 divided by 3.52 squared, and the value you get is into 10 to the power minus 20, 3.52 and to 10 to the power 20, which is about 4 divided by 3.53, 0.322 into 10 to the power minus plus 20, so approximately 3.22 into 10 to the power 19. So we get that. So for this, you need to know additional information is lattice parameter A for nickel is 3.52 angstrom and that nickel is FCC. Okay. Heat capacity. So specific heat capacity. If you remember the formula, it's Q is equals to MC S delta T. Q is heat. Yeah. And Q is energy, so joules. M is, it can be, if it's molar, then it's number of moles. And if it's specific heat, then it's mass. So if you, this is unit mole, this is joule. Delta T has units of Kelvin, and this is a specific heat, heat capacity, sorry. So heat capacity, units of heat capacity would be joules per mole per Kelvin. Okay. Yeah, if you want to imagine. The next layer of atoms is sitting over here, and here. And Okay. Oh, this we already did. Hmm. Miller indices for octahedral plane in a cubic crystal. Uh, Conforms divisor. Okay, so mirror indices of the octahedral plane in cubic system. So this is a cubic system. Octahedral plane are these planes you see these ones. One minus one one and its corresponding. So 1 1 1 is the octahedral plane. Yeah. And this is another question. Calculate number of atoms per unit area in iron crystal on a 1 1 1 plane. So we have assume FCC again. Iron is the FCC structure, has a FCC structure. And 1 1 1 is the closely packed plane. So closely packed plane. Planar density comes out to be 2 over root 3a. FCC. Yeah. Yes, sir. So if you imagine this plane, you'll see this structure forming a triangle. Number of atoms in this triangle. So you have this is half, this is half, this is half, this is 1 over 6, means of 60 degrees, 6, 1 over 6, so half plus half, 1 plus half plus 1 over 6 into 3. 3 again half, so you get 2 atoms. And this edge is 2 root 2a, so root 3 by 4a square, the area of this triangle. So to substitute that area equals to root 3 into area, side length of the triangle, a 4, so root 3 a square by 2. So to get the L, have 2 divided by area 3 is. If you use primitive rounders, then you get this value. And if you use hexagonal, with this value. So this is you get hexagonal planes. You cut it, then you get this value. So this is a more commonly used formula for number of atoms in one plane. 2 over root 3 e square. And the lattice parameter for iron is 3.09 angstrom. If you substitute the value 3 3.09 into 10 to the power into 10 to the power minus 10 squared. So this is about 1.21 into 10 to the power 9. Coordination number of closest packed crystal structure we saw. mm, the FCC you can another way to draw the FCC is the edge centered version. So So you all know FCC is face center cubic. So a cube with atom sitting on the edges and atom sitting on each of the faces. But another way to draw the same FCC is one atom sitting at the center and four atoms sitting on all edges. So these are both equivalent FCC. Just you just have to imagine this with respect to this face center atom. Mm, these four atoms here, you can imagine them as like this one, these four edge ones. Okay. So it's easier to count the coordination number in this structure. So this is center one. It's bonded to four of these. Four on the top. One, two, three, four. Four atoms in the middle. Two, three, and four. Next four at the bottom. One, two, three, and just like four. So 4 plus 4 plus 4, 10. The coordination number for closed packed crystal structure is 12. Coordination number is just number of nearest neighbor. So for this center atom, the nearest neighbors at equal lengths are 12. Determine the Miller indices of a plane that makes the intercept 4 angstrom, 3 angstrom, 8 angstrom on coordinate axis of orthorhombic lattice, whose ratio of axial length is to B is to C, 2 is to 3 is to 1. Okay, so okay. So this is your direction, your orthorhombic unit cell. Okay. So this is 1, this and this 2, and this length is 3. A is A, is B, and this is C. So intercept at 4, yeah, 4 angstrom, 3 angstrom, 8 angstrom. For X, for A, it's intersecting at twice this length, so somewhere over here. Okay. For B, it's intersecting at 3, which is this vertex of this plane. And we just need the third point, which is 8, which is 8 times this length. So 8 times will be somewhere maybe up here. Yeah, 8 angstroms. So if you join, it's too far apart. And make things simpler for us. Noticing it's apart. Okay, so let's assume this one is somewhere over here. Okay, 8 angstroms. It is somewhere over here, but yeah. So, yes. And yes. Now this exactly. Now we have to find Miller indices of this one. So Miller indices A by alpha, B by beta, and C by gamma. So A, B, C are given. So 2, 3, and 1. Divided by your intercepts. At alpha it's 4, beta is 3, and gamma is 8. And this becomes 1 over 1. 1 over 2. Now you can work it to integers. So multiply all these three. You get 1 over 2, 1, and 1 over 8. So you multiply all these by 8. So you get 4, 8, and 2. Oh, sorry, 1. Sorry, 1. Now this becomes your Miller indices. 4, 8, 1. Okay. So for the following reaction, the 25-degree delta H is equals to this. Delta H is this. Delta G, we have to calculate the delta G for this reaction. Okay. If you remember basic thermodynamics, delta G is equals to delta H minus T delta S. So delta H minus T here is in Kelvin. So 25 plus 273 is 298. Okay. Okay. The delta H we are given is 115 kilojoule minus T is 298 here into your delta S, which is 125 joules per K. So kilojoule, you need to convert it into joules. Or the final answer is kilojoule, so let's keep the kilojoules as it is. Kilojoules and 298 into 125 divided by 1000. So this also becomes kilojoule. And this value 298 into 125 115 minus 37.25 kilojoule. This becomes 77.75 kilojoule or approximately 77.8 kilojoules. Another thermodynamic question, which are the following thermodynamic properties is not a state function. So state functions are properties which do not depend on the path taken, and entropy is dependent on path, enthalpy is also dependent on path, and since these two are dependent on path, means free energy is again dependent on path. Right. I'm saying the opposite thing. State function is independent of class. Okay, okay, okay. So all these things are path independent. So below the definition. State function is a property of a system that depends only on the current state of the system, not the path taken to reach that state. Work, if you know, this depends on the path you take. So if you're assuming friction, work is friction force F into ds. So if you take a long random path, your ds, the value of ds is you just integrate it all over the path, becomes longer, and if you take this direct route, it will be lesser. So work done by friction is force into displacement plus path differences. This is just one example. Work done by piston is again path dependent function. So this is a path function. It's not a state function. The equilibrium melting temperature of a metal at 1 atmosphere pressure is 400 degrees Celsius, and the latent heat of melting at this temperature is 1000 joules per mole. Calculate the entropy of melting at 400 degrees Celsius. 0 is 400 plus 273, 673. Okay. 1000 joules per mole. Right. Temperature is 1000 divided by 673 is about 1.49 joules per mole Kelvin. Entropy is Q equals to latent heat Q delta T is latent heat. So delta S fusion is delta H fusion divided by P Delta H fusion is your latent heat in yes, it's the latent heat in this case divided by your temperature. Uh, and this value. Okay. I'll go to the side. Yes. Right. First question was which of the following statement is true regarding the interface of nanomaterial? If you assume you have a nanosheet, uh, your atom setting. So interface are the region with no physical or chemical properties. Interface is just this region between the two, between the bulk material, if you have some thickness, so your bulk and your whatever other medium you have, maybe gas or liquid. The region between them is your interface. So, so comparing it to bulk, where the atoms are sitting happily coordinated with all coordination is complete. The atoms sitting on the surface have incomplete coordination. They have distinct, their properties are different from the bulk. Now we can eliminate other options. Interface, no physical or chemical properties. So since these are unfulfilled, the valency is unfulfilled, so they're only bounded in these five directions. The vertical direction is incomplete. The bond here is incomplete, right? So it is reactive, so it has chemical properties. Same properties as a bulk material, it doesn't. Since again, you can saw that the blank bulk has valency complete and this one has incomplete valency. Trace only present material in specific shapes. Any shape particle you have, there's a interface uh, which is due to the atom sitting on the surface. So every uh, material has a surface distinct property compared to other material. Why surface energy a significant factor in nanomaterial behavior? Okay, so again you have your spherical particle, atom sitting on the surface. You saw they have incomplete valency. So since they have incomplete bonds, they want to form bond along this direction. on along the surface. So they are highly reactive and they want like H water may want to absorb on the surface. So they promote reactions to take place. Maybe O2 water atom would try to bond. Okay. So it actually leads to increase in reactivity and decrease in stability. So for the surface atom, the reactivity increases and stability decreases. High surface energy leads to increase in reactivity and decrease in stability and instability. Increase in instability. Surface energy is not relevant property for nanomaterial. Absolutely incorrect since for nanomaterial, larger fraction of atoms is sitting on the surface, so this is playing even more prominent role as compared to bulk. Surface energy only affects the color of nanomaterial. Now it affects its chemical activity, like catalytic activity, and what else? How it behaves with the environment, chemical properties, those are also affected by the surface energy. The shape is also affected by surface energy, as we saw. Right? What is the term used to describe the process where nanoparticles fuse together to at their surface to reduce the overall surface area? We'll go over all the definitions. So agglomeration happens usually in bulk. It won't can happen in small particles, but agglomeration just means everyone is just sitting together forming a cluster. They're not chemically like uh, bonded to each other. There's a distinct layer in between those two atoms, these two particles. Aggregation, formation of number of things in the cluster. Again, this is forming clusters. Coalescence is again similar thing where you have cluster uh, particles coalescing together to form a larger cluster. Centering is the correct term where the two particles come together and due to diffusion there's a neck formation and over time this neck becomes thicker and these two particles fuse together. So due to diffusion migration of atoms from the surface to the interface, the contact point, you get centering. What is the general name of structure which is formed when a single layer of carbon sheet is rolled up? So carbon sheet, there's just carbons in hexagonal pattern. If you roll up, you get your carbon-carbon forming hexagonal on the surface. Yes, 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 yes. Yeah, inner tube. Since it's hollow in the center, nanowire, nanorods, both are solid structures where there's no hollow, empty space inside. Whereas if you roll this up into the sheet into a cylinder, you get a tube, nanotube. Surface to volume ratio. Um, First one. So surface to volume ratio, yeah, volume, surface area to volume ratio depends both on the thickness of this layer, thickness of the surface layer, and the particle size, which is R. So both. Next question. Sixth. Again, we saw whenever you have this surface, there are bonds, broken bonds. So the more number of total number of bonds, the more is the surface energy. The different planes would have different density of these broken bonds. The total number of unsatisfied or broken bonds present on the surface. Total area of the surface. The larger the area, you will take the more surface energy it will be. Surface energy is defined per unit area. Total number of atoms present on the surface. Mean. Yeah, yeah. So it's not just the atoms, it's total of number of bonds broken. You may have an atom sitting with complete I mean, with completely satisfied bonds. We're more interested in the broken bonds. Surface energy of a spherical particle varies. We had your formula. Surface energy of a nanoparticle. So use equals to m by rho to gamma into a by v. A by v is a surface to volume ratio. Surface energy depends. Definitely, and this is correct. Particle size. No, anything which should be inversely proportional to particle size. If you this is like dimension square, like length square, and this is length cubed. So overall, it should be 1 over d. Hyperbolic curve, parabolic curve. So the parabolic curve. Yeah, that's very slow. I try to look up at the relationship next class. Yeah. Around like with what? Radius, mass is linear to molecular weight, inversely proportional to density, usually inversely proportional to the diameter. I know. This is what respect it's asking for parabolic curve. How do vacancies affect the surface energy of area? So vacancy is just sites where your atom is missing. So surface. This is a vacancy. So again, now these atoms surrounding it have unfulfilled bonds. Since it has unfulfilled bonds, it will increase the energy of the system. Uh, increases the vacancies, increase the surface energy. Okay. Mhm. Now this we already saw vacancy concentration. So if you had these two particles, here you had much higher vacancy concentrations. These are all wicked sites, filled ones. Here we have comparatively less number of vacant sites, so vacancies will shift this way, and mass atoms particles will migrate this way. So this is for the process of sintering. Yes, the difference in the vacancy concentration in the material leads to sintering of the nanoparticle, as there is surface curvature difference, which allows for mass migration, migration of atoms. B is correct. Yeah. Mm, yeah, so it's 20th. Next assignment is due on 20th. To complete it. And I think they have extended deadline for course registration. Check it out. I'm interested. Till 22nd. The second is what? This Friday. The registration is extended till 22nd. If you're interested, you go ahead. That's all to cover. Thank you for attending. If you have any doubts, like post them in the Q&A session. If you are in a discussion group, we'll try to answer it there. Okay. Thank you.